Hi, my name is John Mount. I'm a consultant and a trainer at a company called WinVector. WinVector is a data science company that does consulting, training, and research. And today I'd like to talk to you about a really neat mathematical machine called Bayes' law or Bayes' theorem. So Bayes' law is a very neat way to organize probability calculations. And it's very fundamental, one of the first theorems you can prove once you have your axioms of probability. And you don't even have to memorize it because it's so close to the definitions. So let's go ahead and derive Bayes' law. So P will be our symbol for probability calculations. And this is the symbol probability of A given B. So this is the probability of seeing A happen, knowing we're in a universe where B has already happened. And this is, by definition, the probability of seeing both A and B divided by the probability of B. And we're going to assume that all these quantities are always non-zero. So it's basically simulating a sub-universe where B is known to happen. By symmetry, the probability of B given A is also defined as the probability of A and B. I'm using the fact that P, A, and B equals P, B, and A just to write these the same, divided by PA. So this time we're pretending A is the whole universe. Now, we can derive Bayes' law from this by matching these shared terms. So for the top equation, we multiply both sides through by PB, giving us P, B, P, A given B equals this term here. And we can do the same for the second equation. We multiply through by PA. So PA times P, B given A, and we know these two are equal because they're each equal to this shared term here. Now we divide out PB to get our final form. PA given B is equal to PA, PB given A over PB. This is basically saying how much more plausible A becomes given B has seen is proportionally equal to how much more plausible B becomes given A seen. They both increase and decrease together. This first term here is called the prior, and the whole purpose of Bayes' law is to flip this A given B into a B given A. Maybe we know this one, we'd like to know this one. This denominator is usually eliminated through mathematics. It's usually something hard to determine. Now, what I've gotten more interested in lately is that Bayes' law, we always have taught think in terms of probability. But more recently, we've basically been coming to the conclusion, calculate in terms of odds. That is much, much easier than calculating in terms of probabilities. So give me a second to get some space. Okay, now that we've recovered the space, we repeat Bayes' law is P, A given B equals PA, prior probability, times the flipped version, PB given A, divided by PB. This is Bayes' law. Once we trust it, we don't need the derivation. I find the derivation easier than remembering it. Now, what we're going to do now is work in terms of odds instead of probabilities. Now, probabilities are statements like 2 out of 7 of the weekdays are weekends. So if we pick a day of the week uniformly at random, we have a 2 in 7 chance of picking a weekend. Odds, write this as this, 2 to 5. So basically this is a compressed way of writing the fraction, 2 over 2 plus 5. So this is the odds, if you pick a day of the week uniformly at random, of picking up a weekend. So in odds form, Bayes' law can be derived in a way that's really quite powerful. So let's write down the odds ratio. Let's write down this odds ratio. P, A given X to P not A given X. X is going to be any condition, possibly even an empty condition, making PA given X just PA. Now, what we're going to do in odds worlds is we'll multiply by this arbitrary expression here, P, B given A and X to PB given not A and also X. So you can see these are the conditional statements like in Bayes' law. We multiply odds just like we do fractions. This times this and this times this. So let's go ahead and write that down. And then PB given A and X is how like is B given that we know both the facts A and X. So that gets us these two multiplied together, give us this. Now, odds ratios are not affected by scaling, so I can divide both sides of this odds ratio by the same quantity, which I'm going to divide by PB given X. This is the odds of seeing B given only the X information. And again, X may be no information, so this might just be PB. So we've divided both sides of this odds by the same quantity. So it's the same odds, just like 2 to 5 is the same as 20 to 50. Now, look at this. This is exactly the left-hand side of Bayes' law with a slightly larger x carrying around, which is not a problem. So this is equal to slight extension of Bayes' law, PA given B and X. This is the same thing, except for not A is in the role of A everywhere, so it's just a string substitution, and it's again P not A given B and X. So what we've seen in odds world, if we take something like PA given X, multiply it by something where A is in the right-hand side. All the right-hand side of here is here, plus this is on the right-hand side. Then the multiplying the odds ratio is just an engine that moves the B into the right-hand side, letting us get these conditional probabilities. So this part we don't need to see. It's this is equal to this. This is the odds ratio version of Bayes' law. Now, the reason this is so handy is it's incredibly quick for calculation. So I'm going to recover a little space and then continue. Okay, so this is our odds version of Bayes' law. Cleaned it up a little so we can see what's going on. So how do we use that? Well, we can use that with a really cool puzzle called the Adventure of Silver Blaze. It's essentially a Sherlock Holmes mystery, and in this mystery, in this mystery everyone thinks somebody broke into a stable and tried to steal a horse called Silver Blaze and murdered the groom to do that. So killed the horse's tender. Because the evidence is the horse's tender is found dead and the horse is missing. So this is a really fun one for Holmes because he does this sort of clever pun that the inspector asks him if there's anything unusual clues that Holmes would like to share, and Holmes does share that. He says, yes, the unusual thing was the behavior of the dog. And they go, well, what did the dog do that was unusual? And he says, oh, that's what was unusual. It did nothing. And what he's doing is saying it's the dog that didn't bark. That if a stranger had come to steal the horse, the dog would probably bark at a stranger. And so that's a logical deduction, which is how Holmes works, but we can also do this probabilistically using this odds version of Bayes' law. So let's go ahead and take a look at that. Bayes' law, we're essentially dealing here with what are called subjective probabilities. So let's load some up. To run this example, we'll have to load up what is the probability the dog knew the person. We'll call it knowing the person the event K, odds to didn't know the person. So let's say that's 1 to 3. And that's pretty unfavorable odds. We're kind of stacking the deck to saying maybe this clue isn't going to work, but it really does work. So this 1 to 3 says of the people that visit the farm or the stables, the dog knows 1 in 4 of them, which is a minority, which is kind of weird because most people are probably repeat visits. So this is really a pessimistic estimate. Now we'll also enter in our knowledge of the dog. And we'll say the probability the dog doesn't bark. So we'll use B for the symbol barking. And we'll write the odds of that, the probability the dog doesn't bark given it doesn't know the person. So numbers we can substitute in for that. Well, let's say the dog is well behaved, so it actually usually does not bark when it knows the person. So this probability is quite high. The dog is usually quiet when it knows the person, but the dog is also vigilant, that it very much barks when it knows the person, so it's very unlikely it doesn't bark at a stranger. Let's do our odds version of Bayes' law, and it just says if we multiply these two, then the following symbolic transform happens, that this times this becomes P no given not bark to P not no given not bark. So we're using the fact that this is a transport machine that converts statements like these pairs into statements like these. So it's just pattern matching. This is what we would get. Now for the numbers, 1 times 0.9 is 0.9. 3 times that is 0.15. This is essentially a 6-to-1 odds. Again, I just rescaled by multiplying that this number is 6 times that number, which means essentially the odds that the person was known to the dog are about 6 over 1 plus 6, or 85.7% chance under these modeling assumptions, which again quite arbitrary, that the person, if there was one, that came to the stables was known to the dog, because this is how likely that is given the very unusual behavior of the dog not barking. So that is a great little way we can do the reasoning, and we've seen this sort of in science fiction a couple times, which is kind of sort of fun. So as an example of this, we can show one of my favorites, Mr. Spock from the original series Star Trek, talking in terms of odds. We don't know how he did his calculation, and it's probably a little silly, and it's probably not real, but let's take a quick look at that.
Mr. Spock, you are second in command. This will be a dangerous hunt. Either one of us, by himself, is expendable. Both of us are not.
Captain, there are approximately 100 of us engaged in this search against one creature. The odds against you and I both being killed are 2,228.7 to 1.
2,228.7 to 1? Those are pretty good odds, Mr. Spock.
And they are, of course, accurate, Captain.
Of course.
Now, again, we don't know how Mr. Spock did his calculation, but if he has some premises and his amazing mind can do all the calculations we've done on the screen without needing a screen, it's possible. Now, another example of this was from Star Wars Rogue One, where this robot, we can actually see it, even though it talks in probabilities, which again, we can convert odds to probabilities just by dividing one of these by the sum. A robot that talks in probabilities, and notice its behavior looks very much like an update of beliefs when the character that is supposed to be guiding them there expresses inconfidence on where they are. So that's a cute little clip just for fun.
There's a 26% chance of failure. How much further? I don't know, I'm not sure. I never really come this way, but we're close. We're close, I know that. Well, now there's a 35% chance of failure. I don't want to know. Thank you. I understand.
So both those clips were just for fun, but basically Bayes' law is a core data science, machine learning, probability AI concept. User tends not to have to use it because it's usually basically wrapped into the models we use, that they are doing inference. They're basically taking simple, unconditional things, what are the odds of this being the right deal, and calculating very much more refined conditional odds. So we usually don't do this calculation because it's done by our machines. Most of what we do are frequentist checks of the accuracy or reliability of these mechanisms, but this is a really essential thing. And because of that, how to calculate by hand is a bit neglected. When we get back to how to calculate by hand, I would say basically use odds notation to do that. It's much, much faster than using probabilities. With probabilities, you have to do the calculation twice and renormalize, but that's exactly what's implicit in odds. And this is probably why odds have been so often used by gambling and finance, is that they're basically much easier to calculate over probabilities. You can do things like multiply odds, and you don't have this constriction that they need to stay within a range of 0 to 1. They just need to stay non-negative. And it's basically much easier to calculate with odds, and you'll get the same answer you'd get with your probability calculations, but a lot more of the work is done for you. Anyway, I thought that was a fun thing to go over, and my name was John Mount, and again, I'm from WinVector LLC, a data science company, and we would love to do some work or training with or for you. Thank you very much for your time.